Swayam Prabha. Digital India. Educated India.
Good afternoon. So in the last class we had talked about several acoustic elements. We had developed relationships which were analogous for resistors, inductors and capacitors. Something similar to these electrical elements, we had developed acoustic elements: acoustic mass, acoustic inductor or compliance, and then an acoustic resistance. Where we left in the last class was that we still have not developed some elements which bridge the gap between electrical and mechanical. So in mechanical we have elements which behave very similar to electrical elements, and then in acoustic realm we have elements which behave very similar to mechanical elements. But how do you convert from jump from electrical side to mechanical side and mechanical side to acoustic side? That piece is missing. Those specific elements we call coupling elements. So we'll talk about those today. Coupling elements. And these could exist between electrical and mechanical realms, electrical to mechanical, or they can exist from mechanical to acoustic. Similarly, they can exist between mechanical and piezo, and so on and so forth. So in today's lecture we will cover basically these two coupling elements, and these are essentially transformers. So they transform one form of energy into another form of energy, or transducers. So we'll start with electrical to mechanical coupling. So let's consider a magnet, and this is its north pole, and then I have the south pole, this is my south pole, and there's a gap between the two poles, and what you have is a conductor passing through it. And let's assume that the current it is having which is flowing through this is I, and there's a potential difference across the conductor. And because there's a north pole and a south pole, you have a magnet. There's this magnetic field which we label as B, and this is my axis system. XYZ. So this B has several names. So some people call it B field. Others, especially electrical engineers, they call it magnetic field density. Electrical engineers call it. I think a B field is typically used by physics people. There are still others who call it magnetic induction. Magnetic induction. And then there's one more name in prevalence, it's called magnetic field. So notice it's magnetic field density, but some people also call it magnetic. And the units for this are Tesla in SI system and Gauss CGS system. So just some nomenclature. So we know from laws of electrical engineering that force, so when you have a conductor through which current is flowing, and that current is cutting across a B field, then this conductor experiences a force. From laws of electromagnetics we know that. And that force, which is called Lorentz force, equals B times L, where L is the length of the conductor, times current. And the potential difference across this conductor would be voltage equals B times L times velocity. So this is all standard electromagnetic, and your V is your back EMF and U is velocity. B is magnetic field density, L is the length of. So from these two relations, if I have an electrical circuit and if it is coupled to a mechanical circuit through this, what you can call it a motor, which converts electrical energy into motion, then I can make a transformer something like this. So I have voltage being applied across this thing, there's a current going through this, and this voltage gets converted into velocity, and my current is getting converted into force, and the turn ratio, voltage equals BL times U. So my turn ratio is BL. So I can on this side put all sorts of inductors and capacitors and resistors, and I can have as complex as an electrical circuit I can have. And here I can have in this, on this side, whatever number of mechanical elements which are there in real system. And if I have to compute force, if I introduce this element, this particular coupling element, then I am able to convert voltage into force and I into, voltage into velocity and current into force for mobility analogs. If I have impedance analogy, then I have the same equivalence, but my turn ratio will become 1:BL. You can do the math. Also in that situation, my voltage will be the through variable and my current will be the across variable. And similarly on the mechanical side, force will be the across variable and velocity will be the through variable. So this establishes an equivalence between electrical and mechanical reams. So this is like a coupling element. So current goes in, you also excite it with the voltage, it gets converted into motion through this transformation, and then that motion later gets converted into sound. So now we will develop a coupling element which joins acoustic and mechanical networks. So again, I have a transformer and if I am using the mobility system of equivalence, then my across variable is velocity, or actually yeah, and my through variable is force on the mechanical side. And on the acoustic side, my across variable is volume velocity and my through variable is pressure. So from here you can see that VV, we know that VV, volume velocity, is essentially velocity times area. Area of what? Whatever membrane or surface which is pulsating, it's the area of that surface, and it is actually normal to the direction of motion, because volume velocity is a dot product of area and velocity. Also, we know that pressure equals force over area. Simple. So again, you have this. So my turn ratio will be related to area, and so your turn ratio is 1:8 in this case. So this is my coupling element for acoustic and mechanical circuits, and this particular ratio is valid for mobility equivalence. If my equivalence is of impedance type, then again these relations are still holding, but my this ratio will become A:1 rather than 1:8. So this is the last piece in the whole puzzle. So now we know how to construct an electrical circuit. So I can have an electrical impedance, and then I can have a transformer. If that current is getting, yes?
Even if impedance can allow,
Hmm.
the turn ratio will be the same. Now. Just we are changing the through variable and cross variable interchanging.
Yes.
Turn ratio will then also come out to be
The turn ratio becomes inverted. So when you do the actual math, you will see that it becomes 1 instead of 1:8.
So why f will always be p times a. Now whether f comes as a through variable, then also it is also
If
p
you
times.
so to explain in electrical transformers, V times I.
So we know,
The ratio
not
of a
changing-
cross variable is turn ratio and ratio of through variable is inversely proportional to.
Yes, because V times A is preserved. Voltage times I on one side of the transformer is same as voltage times I on the other side of the transformer. So if you switch those, then your turn ratio becomes
So
inverted.
like here if you switch f and u,
Huh.
sir, f will come as the cross variable.
F will become the
across variable and
yes.
u will become the through variable.
Yes.
And the same side also,
Yes.
VB will become the through variable and P
Yes.
will become the cross variable. Across
So-
variable. Again,
Yes. So okay. So when you have a step-up transformer where voltage is going up, right? Your N1 and N2 has to be more than N1, right? And vice versa. So if you use, so we'll explain it a little later. Maybe after the class we can go over it in a little bit more detail. But believe me, this ratio gets inverted, and we'll show it very clearly mathematically. I have wanted to cover a couple of other things, but we will explain it in more detail later. So what we have talked about is the coupling elements, and that essentially in a very general sense completes the picture. So you now have equivalences between electrical, mechanical and acoustic parts of the entire circuit. You can use similar philosophy if you have a piezoelectric transducer and develop similar equivalences, and so you can develop similar coupling elements between piezo and mechanical or piezo and electrical rings. So the idea of showing all this exercise at this detailed level is, one, to help you understand how these interdisciplinary circuits are constructed, and B, if you run into some other transduction processes, then you have at least a thought process which you can use to develop similar equivalent variables in other realm of engineering. So now we'll talk about something called a Helmholtz resonator. Okay. So in mechanical world, you have a spring and there's a mass, there's a spring, and if it moves on a frictionless surface, and if I perturb it by a small distance x, then it oscillates at a natural frequency omega equals k over m, or the frequency will be 1 over 2 pi times k over m. You can have similar acoustic compliance systems in 1 degree of freedom in area of acoustics. That is called a Helmholtz resonator, that particular device. Physically, what it looks like is, in a very general sense, you will have a volume and you will have a short tube. And in mobility analogy, we saw, not mobility, this volume we know it acts as a spring physically. And we know that the air in this tube, it acts as a rigid mass or an acoustic mass. We talked about it at length. So again, you have a mass and you have a spring here. And this has a tendency to resonate by itself. So if you have, one of these soft drink bottles, and they have a little bit like this, and you blow over on top of it, you'll hear some sound coming out. That is essentially the natural resonance frequency of this bottle. Maybe in one of the exercises we'll ask you to calculate what is that natural frequency. And essentially what's happening is, so again, very similar to a mass and a spring system. If I push the mass, the spring gets compressed, and let's say that is my steady state condition, then I release the force on it. So then the mass moves out, but then it, because of inertia, it goes above and beyond the neutral position. So then the string goes into tension, so, and at a point when mass stops moving, the spring pulls it back, then the mass comes back, and again it exceeds the neutral position, it compresses the spring, and it goes back and forth. Similarly, if you press a bottle or a device, something like this, if you press the air in it, and after a time you release that pressure, all of a sudden, the air, the mass in this, acoustic mass in this part will move back and forth. And in theory, it will move back and forth for infinite amount of time at a natural frequency, which we will calculate, because you have a spring here and you have mass here. So some other shapes, another shape of a Helmholtz resonator could be like this. So this is again, you have an acoustic mass element, and here you have a spring. So if I want to understand this and solve for its natural frequency, I can, if I use mobility analogy, then this is my inductance, which acts like a spring, and the value of this is rho naught c square. And this is my capacitance, which behaves similar to a mass, and the value of this, as we developed in the last class, is rho naught L over A, where A is the cross section of this tube, cross sectional area of this tube. This is my L, and cross section is rho A. So total impedance between these 2 points is j omega times V naught over rho naught c square plus 1 over j omega rho naught L over A. Now for resonance, Z equals 0 in this case for resonance conditions. So j omega V naught over C square equals 1 over, I can bring my A up, j omega rho naught L minus, and then I can eliminate the negative sign by bringing j up in the numerator. And now if I solve for omega, essentially what I get is omega equals C times cross-sectional area of the tube divided by length of the tube times V naught. Is that what I get? Yeah. Okay. I can use this Helmholtz resonator in a lot of ways. It has its applications. We'll talk a couple of applications about it. The first application where it is used a lot is in sound systems. So we will draw two boxes. So I can have a box A. Excuse me. And it has speaker mounted here. And it's a sealed box. A lot of traditional boxes you have a speaker and it is sealed. You may have seen it in your homes also. And you try to measure the pressure at this location over a frequency range. And then another system you can have is again a sealed box with a Helmholtz resonator, and we'll see what it does. So I still have exactly the same transducer, but here I have a port also, or a tube. Okay. When I plot the frequency response for system A, and this is my system B, typically when you do the actual measurement, and in later parts of this course you will actually develop relations which will show. So if I am plotting pressure at this location, SPL, and I am plotting it against, let's say, frequency, it will be something like this. And just to put some numbers, let's say this is 85 and this is all decibels, and this could be 100 hertz. And note that this is a decibel scale. Okay. So a drop of 6 dB is a big change. 6 dB means like twice the energy content is 2 times less in the whole system. So if this drop is 6 dB, essentially what it says is that at 100 hertz, at maybe a higher frequency it's producing 85 dB, but at 100 hertz it's producing 6 dB or even less than 6 dB from that 85 dB threshold, which is not a good thing, which means that low frequencies, bass frequencies, which people like to hear more of, they are not being produced at an equal level. So to solve this problem, what people do is they introduce a Helmholtz resonator in it, and it's a very inexpensive solution. They just introduce a tube in it. So you have a volume here and you have a tube, a port. So you have a spring mass system, and what it does is that because of the resonance, and they tune the length of the port and volume in such a way that the resonance is below some number. Let's say if I want to improve performance at 100 hertz or 80 hertz, then I tune this in such a way that my resonance frequency is at around 80 hertz if I want to improve the performance at 80 hertz. So when I do that, this transducer is producing SPL something similar to that, but my resonator is producing a heightened output at 80 hertz wherever I am tuning it to be. So for on 80 hertz, whatever is the tuning frequency, and in the neighborhood of that, I get a little bit of extra push. So I improve my bass performance. So once you have, so this is A, and once I put a Helmholtz resonator, so this was something like this. Once I have a resonator, it could be something like this. So I have increased my frequency content, the magnitude frequency in this range. And on the negative side, you have a steeper slope on the low frequency end. So you start killing lower frequencies than a certain threshold much more steeply, but you are able to get some extra bass in this area. So a lot of sound product companies, they use these pipes. So you have a sealed volume, they put a pipe, sometimes they put 2 pipes to add extra content for specific frequency bands. So this is first application. Another application is in musical instruments. So we'll see 2 pictures. This is one of the quote unquote original Helmholtz resonators constructed by Mr. Helmholtz in around 1850s. Okay, so you have volume and you have a little bit of a tube here. Now look at, so this was 1850s. This is the picture of Veena. So you have 2 pictures of Veena. And these round big spheres are essentially some hollow, either pumpkins or locky, that gourd. So traditionally they would hollow it out and they'll have a small tube going up. And this, they have been using it over at least last 2000 years, because people in ancient drawings also, people have found pictures like that. So people have been using Helmholtz resonators prior to birth of Mr. Helmholtz. This is a very long time. Other thing is, this is another Veena called Kinnari Veena, and it has 3 resonators. So again, these resonators increase the performance at specific frequencies. Right. So in this Kinnari Veena, it just happens that this is a picture of a Veena which is sitting in a museum in France. It's an instrument which was made something like in 18th, 19th century. And some French sound engineers and scientists, what they found was that they found the tuning frequency of this little pumpkin and also the larger pumpkin, and they found that the ratio is 2. So they are off by 1 octave. So even in earlier times, people had a very clear understanding of octave. This is a proof. It's sitting there in the museum. You can go and measure it if you want. People had a clear understanding of octave and also had figured out how to tune so that the natural resonance of one resonator is twice or half of the other resonator. So this is, so again, in a lot of musical instruments, in guitar, there's a hollow box below the string. Now you will not see an explicit tube in a guitar, but we'll talk about it later. That hollow box also kind of acts as a resonator. So that is another application of the same resonator. Third application is in air boxes. So in engines, earlier air used to go to a carburetor, and then there it used to get mixed with petrol, fuel, and then it used to get. Nowadays, people are using less of carburetors and more of air boxes. And there also the aim is that if they can figure out somehow as a way to smartly suck air more efficiently into the system, then it requires less energy. So again, they use concepts rooted in the idea of a resonator, and they suck air. Another example is, and we'll do some math about it, is architectural acoustics. So you have a big hall and someone is playing music or speaking, and if the walls in the hall are parallel, then you can have standing waves because they are parallel, and the wavelength of those standing waves will depend on the distance between the two walls. So we saw earlier, if you have two fixed structures, they could be a standing wave. So people try to eliminate those standing waves because those standing waves are not pleasing to hear by using resonators. So in the first three examples, in case of a loudspeaker, in musical instruments and air suction, we used resonator to enhance the frequency performance for certain pitches, for certain frequencies. In case of architectural acoustics, they use the same tool to kill specific frequencies, and we will do a little bit of math around it and see how it does. They accomplish it. So let's say that we have a long tube, and the cross section area here is A1, here it is A2, and here the cross sectional area is A3. Also this length is L1, this length is L2, and this length is L3. And then I have a big volume here, not necessarily big, a volume here, V0. And I'm sending signals through this side. Let's say the volume velocity is Vv. And then there's a guy sitting here, observer. And he is measuring VO. Okay. So this combination of volume and this small tube on top of this circle is your resonator, right? So the question is, find VVO over VV. So we draw an acoustic circuit for this. So in this case, because VV happens to be through variable, we'll use impedance analogy. So my pressure is analogous to voltage, and VV is analogous to current. This is impedance approach. Impedance analogy. So now I construct a circuit. So essentially I have two tubes, short tubes here, another short tube here, a volume here. My volume in impedance analogy will be modeled as a capacitor, and my tubes will be modeled as inductors. So let's say this inductance is L1, L2, L3, and this capacitance is C. So my L1 equals rho naught times length of the first element over A1. L2 is rho naught L2 over A2. L3 is rho naught L3 over A3. And capacitance is volume over rho naught C square. Okay. The through variable, as we talked, is VV, and here I am measuring VV naught. So the question is, what is VV naught over VV, magnitude of this? Okay. So at a very subjective level, when the frequencies are very low, how will VV get split along these two paths? VV will split at this junction. Some of it will go through L2, some of it will go through L3. But when frequencies are very low, what do you think will be the magnitude of current going through this circuit, the L3C? It will be virtually zero, because impedance offered by C will be very high. So for very low, omega VV naught is approximately equal to VV. So my ratio is 1. For high values of omega, there will be some, okay, so at very high there will be virtually zero current, but what we are interested is what will be the ratio of VV naught over VV. So whatever little current is going, how will it get split in the two directions? That is the question. C will be acting as a short circuit, so it will split based on the ratio of L2 and N3. So C kind of acts as short. So whatever VV is going in, it will split like this. The influence of capacitance will be virtually negligible. I am just ignoring that. And if L2 is fairly large, L2 is very large compared to L3. Remember, L2 and L3 are inductances, which are these numbers, they are not lengths by themselves. So if L2 is very large compared, then VV naught over VV over VV naught is essentially L3 over L2. And finally, what will happen at resonance point? So you have this circuit. What happens when there is a resonance in this part of the circuit?
Impedance goes zero. Impedance goes zero.
Impedance goes to zero. So what happens to VV naught?
Sure.
Huh?
VV naught will be zero.
VV naught goes to zero. So at resonance, VV naught equals 0. So VV naught over VV is 0. And the value of this resonance frequency will be 1 over 2 pi times 1 over LC. That is 1 over 2 pi square root of L3 times C. So I, at a very coarse level, I plot this transfer function's magnitude. So I am having here frequency, and here I am having, let's plot it omega. So here I have omega, and here I have VV over VV. So at low frequencies, this value is 1. At resonance, which is 1 over L3C, this value comes to 0. And for the condition, this condition, if L2 is very large, then large compared to L3, this should have been VV naught over V. This is an asymptotic value will be L3 over L2. So my transfer function will look something like this. So in all other examples of the resonator, I was using the resonator to boost the performance at specific frequencies. Here I am using the same device to kill specific frequencies. In this case, something in this band, I am able to attenuate the magnitude of that. So resonance can do all sorts of things.
So in the actual hall, it is the walls are designed that the architectural this thing is designed to kill this frequency. So
this is used to be used especially in earlier times because people didn't have a very clear understanding of how standing waves are interacting, what is the damping coefficient of different materials at different frequencies. Nowadays, there's a more higher emphasis on the shape of the room, also the damping materials being used, how the speakers are placed in the auditorium, where should people who are generating music or sound, they should sit, all that. The reliance is not that much on resonators, but the point what I'm trying to make is you can use the same resonator in totally opposing, with totally opposing or different purposes. You can boost frequency response or you can kill frequency response.
Yes, I'm just trying to say that the system in the hall, sir, it should also be tuned to produce this frequency so that it can be killed with this.
No, the tuning of the room will depend, as I said, suppose there are two parallel walls and they are separated by some meter lengths. So it's tuned to have a standing wave which is related to that dimension. So it is, in that sense, it is tuned to a specific frequency. So what you want is that those standing waves, they should not be heard loudly by the people sitting in the auditorium or in that listening space. So that is a consequence of the geometry of the room,
Yes.
the natural
Yes,
modes
yes, yes.
of a. So we'll do one more example. This is not a Helmholtz resonator, but just for practice purposes. So I have a tube connected to a volume. Pardon my very poor drawing. And this is connected to another sac. And here you have an acoustic resistance, RA. In mobility, the resistance will be 1 over RA. This is right now impedance model. here the volume is V naught. This is V1, and this I call L1, and this length L2. So we'll very quickly construct an acoustic circuit using impedance analogy. So my across variable is pressure, through variable is volume velocity. It goes through the first tube, which acts like an inductor, such that L1 equals rho naught L1 over A1, and then I have an acoustic capacitor here, or a spring element, which is V1 over rho naught C square. Then I have another acoustic inductance of value L2, such that that being equal to rho naught L2 over A2. And then I have finally one more capacitor. So I should have put a resistance here. And if I do a mobility model, so this is my impedance model. So in my mobility model, I have volume velocity, inductors get replaced by capacitors and vice versa. The values do not change. And the resistor stays the same, but its value becomes inverted. So and this is rho naught L1 over A1, and this is rho naught L2 over A2. So this is mobility model. So in a lot of these circuits, just wanted to recap a couple of very simple but important points. You will see combinations of inductors and capacitors. So you can have a capacitor of value L, an inductor of value L and a capacitor of value C. And when you see, you should start thinking, how is this thing going to behave? So again, for low values of omega, it will behave purely as a open circuit, and the capacitive part will dominate for low frequency. The capacitive part will dominate. For extremely low values, it will become an open circuit. It will go towards an open circuit, but capacitive part will dominate. And for high values, of omega, inductive part dominates. So if I plot the impedance, and this is my omega, the capacitive component will be infinite at 0, and it will fall like this. So here Z equals 1 over j omega C, and the inductive component will grow with frequency, and here Z equals j omega L.
The capacitive part will come from the bottom.
I am just plotting the this magnitude.
Otherwise, it won't come out to be 0. No?
So again, I am just plotting the magnitude of Z. So this is the crossover point, and the value at which these two become equal is 1 over square root of LC. And the last point I would like to make here is all this approach where we are having lumped parameters, doesn't matter whether it's electrical ream, mechanical ream or acoustic ream, they work to the extent that your frequencies are less than compared to lambda over 2 pi. The lengths of the elements are less than lambda over 2 pi. The length of the element is less than lambda over 2 pi wavelengths. So if in an electrical ream you are starting to violate some of this condition, you will not be able to accurately model the electrical circuit using lumped elements, because then they become continuous systems, as we saw earlier in several lectures back in transmission line, as we were developing the transmission line theory. Capacitors stop behaving as lumped capacitors when the wavelengths violate this fundamental condition. The same thing is true for mechanical, and same thing is true for acoustic ream also. So as we are solving some of these equations and constructing these complex circuits, we have to be cautious that in every single ream, are we sticking to some of those guidelines or not. So that is what I wanted to talk today in context of Helmholtz resonator and a little bit about overall electrical circuit. So now I wanted to introduce this notion of acoustic radiation impedance. Radiation impedance. What is it? An electrical circuit, let's say an amplifier, and it's receiving electrical energy. You know how to convert that electrical energy and model that conversion process to mechanical energy. We saw this whole transformation process. Then this mechanical energy gets converted into sound, which is generated by a loudspeaker. And we know how that conversion is happening, and we have developed elements, lumped elements for short tubes, closed tubes, short volumes, and acoustic resistor. Once the sound leaves that box or sound system, whatever, and it reaches my ear, there is some impedance in that travel process also. That is called radiation. So far we have not captured that. If I have to accurately model the entire circuit from source to the listening point or the observation point, that is one last piece of puzzle which is left, and that is radiation. And the radiation impedance will change depending on if you have a sphere which is pulsating back and forth, it will have one type of radiation impedance. If I have a sound source mounted on an infinite wall, the radiation impedance will be different. If it's a sound source just moving back and forth, maybe for some frequencies, low frequencies, the person at the other end may not hear anything, because as a piston is moving forward, it's creating positive pressure on the front surface, and on the back surface it's creating suction. So once those two waves add up and they reach your ear, you will hear very little sound. So all that is about radiation impedance, and that depends on the distance between the listener and the source, how the sound source is mounted, what is the boundary condition at the source point, the geometry of the source, and several other variables. What we will start today is a radiation impedance of a pulsating sphere, because we have developed some relations in past, how sound propagates as it emanates from a simple spherical small source. We have developed some relations, and then in subsequent lectures we'll do some more examples of different types of radiation. So we'll start from the definition of instantaneous power. So instantaneous power, we had talked about it earlier, is instantaneous voltage times instantaneous current, and an acoustic ream will be instantaneous pressure times instantaneous velocity. Right. So it is Pt times Ut. And then in some of the earlier lectures we had developed this relation such that this is equal to P times U star plus real component of Pu E2j omega t. And then the U star is essentially complex conjugate of pressure over complex conjugate of Z, that is Z star, plus half real P, and then again U is P over Z E2j omega t. This one I simplify, so I get half times magnitude of pressure star times real of 1 over Z star plus half real P times P over Z times E2j omega t. In one of the earlier lectures, we had said that Z, which is the impedance, could be a magnitude times exponent j psi, where psi was related to this power factor notion. Also, pressure will have a magnitude which is a real positive number times exponent of j theta. So if I put these two relations in my above equation, I get instantaneous power equals magnitude of pressure whole square times, and real of 1 over Z star would be times 1 over Z times cosine psi plus times 1 over magnitude of Z times cosine 2 omega t plus 2 theta minus psi t square over 2. Yeah. Also, so now this is what we had defined as average power, and this is the fluctuating portion, and there's a psi component to it also. I mean, there's influence of psi also. So when I plot this, and this is to a certain extent a recap of some of the earlier work, for psi not being equal to 0, this is my time axis and that's my power. The total power will be something like this. Where my average power is going to be positive non-zero entity, and this is my total power. And this area below the axis is essentially the energy which is getting dumped back into the system. Also, we had in the last class or one of the earlier lectures talked about that because this is not symmetric along the horizontal axis, the time axis, what it means is that it will eat more than the quote unquote the normal current which would have been needed if cos psi was equal to 1. Because there is lack of symmetry along the horizontal axis, it will consume more power, the case where cos psi would have been identically 1, that is if psi was equal to 0. This was a recap of some of the stuff which we have done. So now, remembering this, we will look at a spherical radiating. So I have a small sphere. We had developed its radiating impedance to be E R0s over U R0s. What this means is that this is the radiating impedance of small spherical source of radiating of radius R0 on the surface of itself. So this is what the body will see as its impedance on its surface. If you move away from the surface, this R naught will grow, will become whatever R value is going. So my ZRA, which is acoustic impedance, is essentially ZR over area. So that is P R naught S over U R naught S times 1 over area. And remember, S is equal to S equals J omega. ZR we had seen was 1 over rho naught C times C over S R naught plus 1, the whole thing inversed. For a purely resistive circuit, the what would be the value of psi, power factor? Psi would be 0. You see here that there is an S component here, which means that the impedance offered by a pulsating sphere is not purely resistive. So whenever you have a pulsating sphere, it will, by nature of its presence, introduce a non-zero psi in the entire circuit, which means that at the amplifier level, it will draw more than optimal value of current, and it will require more than optimal value of voltage. So you are introducing, just because by virtue of that it's a spherical surface radiating in free space, you are introducing a non-zero value of psi. And maybe to fix that at the electrical level, you can put some capacitors or, to rectify that. This is Z naught. If I invert it, where Z naught is rho naught times C times S R naught over C plus S R naught. And if I replace S by J omega, I get Z naught times J omega R naught over C plus J omega R naught. What we do here is we try to rationalize this term. So I get, basically what I do is Z naught times J omega R naught over C plus J omega R naught times, I multiply and divide by C minus J omega R naught, and I also divide it. And what I get is, if I do simplifications, omega square R square over C square plus J omega R naught over C. So I will now plot this. I'll plot its real component and also its imaginary. But before I do that, so I'll rewrite it. ZR equals Z naught omega square R square over C square I think J omega R naught over C.
We are assuming that omega is very,
We are assuming,
because only then these relations will apply.
why?
So because if we do the exact match, there is a omega square R naught square term in the denominator.
So this is Z naught and this is omega square R square R naught square over omega square R naught square plus C square plus J times omega R naught C over omega square R square plus C square. Yeah, that was a simplification. I had done it. If omega is low, then this is my relation. And if omega is large, then I get ZR equals Z naught 1 plus J C over omega r naught. Regardless whether omega is small or omega is large, you have complex imaginary components in the entire term. Except for very low frequencies, what you see is, except for very low frequencies, it becomes purely resistive in nature, and at extremely high frequencies again it becomes purely resistive in nature. But in the intermediate range, it has a reactive component, and what that means is that at most of the operating frequencies, what these two approximations show is that psi will remain non-zero. So power factor will be non-zero, will be not equal to, exactly equal to 1 for most of the frequencies we are talking about. So I'll just plot. So I have here, what I will plot is this is my real component of ZR, and my imaginary component will be something like, it will be an asymptotic. So what this shows is, again, this is a plot of different components for ZR, real and imaginary. This is my omega axis, and what we have shown here is that regardless, except in very extreme conditions, extremely high frequencies or extremely low frequencies, in most of the range, my spherical sources are fairly reactive in nature, which means that if I have to produce significant amount of dB SPLs from these sources, the spherical sources, it is a difficult thing to do because they eat a lot of power at the amplifier level. That is the implication. So if you are designing a complex system, and if you are thinking of using a spherical source, then you have to think a little bit more carefully how you develop a system. So that's all we will be covering today. In the next lecture, what we will talk about is, so this is my ZR. I still have not approximated this into a set of resistors, inductors, and capacitors in the acoustic world. So if I have electrical, mechanical, and acoustic, I have all that conversion, but I still have till so far not converted this into some lumped systems which I can construct in the acoustic range. So that is what we will do for a spherical source in the next class, and then we will also consider a couple of other sources.